Okay, good morning everyone. Naisip ko lang baka hindi pa ako nakapagpakita sa inyo ever. So yeah, on ko muna yung camera ko for the housekeeping matters. So first off, we'll have the final problem set starting tomorrow, December 17. Though hindi ko pa siya nasusulat, crammer din ako. So mamaya ko pa isusulat yung problem set number 4, but it will cover post-its until whatever we will discuss today. And then the deadline would be on December 24, right before midnight. Pero sabi ko nga, kung gusto niyo siyang tapusin before the Christmas break, then you can do so kasi I'll see to it that this is doable or finishable. Finishable yung term. Kaya siyang tapusin by December 21. Um, it will just comprise of 3 questions again. One problem is an essay type problem or yeah, hindi siya it's either essay writing or it's example building like what you did in problem set number 3. Tapos meron siguro dalawa akong ipapaprove na mga statements. And then you can expect that those proving questions will be coming from posits, from maximal elements, minimal elements, least element, greatest element. So those sort of things. Don't worry much about Piano's axiom, the well-ordering principle, Zorn's lemma, or ano pa nga yung isa, axiom of choice. Tapos, wag din kayo masyadong mag-alala about what we will discuss today. Hindi ako magbibigay ng proving questions sa kanila. So more of appreciation questions yung manggagaling dun sa mga topics na nabanggit ko. So probably I'll put them in an essay part of the problem set para matingnan ko lang kung naiintindihan nyo or na-appreciate nyo yung mga pinag-discuss natin dito. All right? So yeah, that's it. And then we still have a final assessment. I don't know. I keep on promising to give you the guidelines. I have the draft guidelines right now, so I'll try to upload the final guidelines for the final project. Siguro by tomorrow na rin kasabay ng problem set. The deadline for the final assessment, which is equivalent to one problem set, is on finals week. Nilagay ko yata sa Nilagay ko yata sa course guide natin ay January 10. So I think we can stick on with that. Either January 10 or 11. Kung January 11 yung deadline ng finals ng Math 101, then doon natin siya i-juju. Pero kung earlier than January 10 yung finals ng Math 101, sige, lalagay ko hanggang January 10 pa rin yung deadline. So it's either January 10 or 11, whichever is or kung ano hindi. January 11 siya. Kung January 11 yung finals ng Math 101 according to the registrar. Tapos otherwise, it's January 10. Okay? Okay lang ba yung timeline na yan sa inyo? And then since the semester is almost at the end, so paki-double check yung mga entries kay Canvas at paki-check kung na-record na doon lahat ng sinabit nyo. Yung mga scores nyo, lalo na dun sa mga estudyante na nagkaroon ng konting problema with Canvas that forced them to submit either by email or via chat ng mga requirements sa amin. So dapat lahat ng grades ay makikita kay Canvas. So kahit sinend nyo siya sa amin via email, yung grade nyo dapat doon ay naka-encode kay Canvas. Kasi ang pagbabasihan namin ng final grade ay kung ano yung naka kay Canvas. So pag na-input namin yung problem set 4 and final project, yung numerical grade na naka kay Canvas, yun yung final grade nyo. So make sure that everything all of your submissions were graded and your scores were encoded in Canvas kasi doon kami magbabase ng final grade nyo. Okay? What else? All right, I think that's all. That's all the housekeeping matters. So balik na tayo sa discussion natin. So let me start sharing my screen. Oh, by the way, I'll also create a what do you call this? A assessment an assessment siguro Google form for you to assess how was the handling of this class this semester. Especially this is a foundational class for you guys. Gusto ko malaman how do you think the course was handled? What are the points for improvement? So I'll probably write a short survey instrument. Siguro ilalagay ko siya as part of problem set number 4 para ma-require kayo na sagutan yung evaluation form na yon. So yeah, it will come. It will come with a problem set. So kindly fill it up for future improvement of Math 101. Okay. So I think we're set, except my pencil is 5% on battery na lang. So hold on, let me turn off my camera, and then let's start. Let me just take one sip of my coffee, and then we'll talk about cardinal numbers. Okay. Now, as I've mentioned, magiging mabilisan yung discussion na to. Maraming terms na kasama. But what I want you guys to build up on is an appreciation of what cardinal numbers are, specifically the concept of infinity. So maraming technical terms. It would be good if you can understand these technical terms. Huwag kayong mag-pay attention masyado sa pag-isip. Paano ko to gagamitin sa proving? So, kailangan lang maintindihan natin, or as the cliche goes, isa puso bawat isang mga terms na makikita natin dito. Alright? And then I'll play a couple of videos along the way para naman medyo hindi ganon kabigat yung last session natin for the semester. Okay? Now, we start off with defining what equivalent sets are. Okay? So, a set A is said to be equivalent to another set B, denoted by A tilde B, or babasahin ko na lang siya na A is equivalent to B, if there exists a bijection F from A to B. Okay? Remember, a function would be bijective if it is both injective and surjective. Or ito yung mga functions na epic at saka monic at the same time, right? Or tinawag rin natin itong mga bijection to be one-to-one correspondences. So kapag ka siya ay one-to-one at saka onto, ibig sabihin bijective yung function, right? So we say na equivalent ang isang set sa isa pang set kung merong one-to-one correspondence between the two sets. So a quick example, okay, would be, say, the set of all the letters in the alphabet. Let's call it capital A. So little a, little b, little c, hanggang z. And then say the uh, the set n, which is the set 1, 2, 3, 4 until 26. All right. Now we can say that the set A is equivalent to the set N because we can define a one-to-one correspondence between the two sets. Remember, para maging one-to-one correspondence, kailangan function siya. So sa bawat element ni capital A, dapat may ibigay tayo na isang unique element ni capital N. Para maging one-to-one correspondence, dapat one-to-one. So ibig sabihin, dapat bawat isang element ni N naka-partner lang sa isang element ni A. Bawal maulit yung mga elements of capital N to be a first element, to be a second element. Diba? And then it should be surjective. Ibig sabihin, bawat isang element ni capital N dapat may ka-partner o may pre-image kay capital A. So yun yung ibig sabihin ng one-to-one correspondence. Now, there could be several one-to-one correspondences that you can define between A and B. The thing is, dapat may mag-exist lamang. So makapagpakita ka ng isang one-to-one correspondence, then that will automatically make A equivalent to the other set B, or in our case, the set capital N. So one such correspondence is, I will assign 1 to A, or A to 1, assign B to 2, C to 3, D to 4, and so on until assigning Z to 26, right? So isa yung bijection. So ito yung minsan tinatawag nating alphabetical relation, where we are assigning a letter to its chronological order o kung pang ilan siya doon sa English alphabet. Some call this the lexicographic order. So yeah, mga technical terms na tino-throw out ko lang para I mean, para may pangyabang kayo sa iba niyo mga classmates, instead na alphabetical order. Yeah, sasabihin nyo, pabida kayo, lexicographical ordering. All right. Now, there could be other one-to-one correspondences, like assigning Z to 1, Y to 2, W, X, Y, X to 3, and so on. So backwards order. That's still a one-to-one correspondence, pero isa lang yung kailangan para masabi na si A ay equivalent kay B. In that sense, we can say that A is equivalent to B because there exists a one-to-one correspondence between A and B. Now, the set B, or the set capital B consisting of the vowels A, E, I, O, U, is not equivalent to N because we cannot define a one-to-one correspondence between, N pala to, between N and B. Kasi si 1, ipipair ko siya kay A, si 2, ipipair ko siya kay E, si 3, ipipair ko siya kay 4, kay I, si 4, mamap ko kay O, si 5, imamap ko kay U. Pero wala nang mga ibang kapartner, yung mga number 6 and so on. And then, it is impossible. It can be shown that it is impossible to define a one-to-one correspondence from the set N to the set B. Kasi para maging surjective siya, dapat lahat, magiging surjective siya, pero kailangan maging one-to-one siya, di ba? So, para maging one-to-one, kasi mas marami yung elements ni capital N, dapat maulit yung mga elements ni capital B to serving as second components para lang mabigyan ng kapartner lahat ng elements ni capital N. So, halimbawa, naubos na siya, 1 to 5, na-assign ko na siya. Tapos si 6, mapipilitan na akong i-assign siya kay A para maging domain niya si capital N. Pero once I assign 6 to A serves now twice as a second component, making the function not one-to-one. So dahil hindi na siya one-to-one, hindi na siya magiging one-to-one correspondence, and actually any such effort will end in vain. So we can say that capital N is not equivalent to capital B. So in a nutshell, we say equivalence is sort of kung magkasing dami sila ng laman. Alright? So yun yung parang konsepto ng equivalence ng dalawang sets. Okay? And the nice thing about the relation equivalence is that it is an equivalence relation, meaning it is reflexive. That is obvious. Si A ay equivalent sa sarili niya kasi magkasing dami ng laman si A at saka yung sarili niya. So one-to-one correspondence that you can use in order to show that a set is equivalent to itself is the identity relation. The identity relation is a bijection, all right? So, and then it is a relation from, or it is a function from a set A to itself. So, yun yung one-to-one correspondence na pwede natin gamitin para ma-prove yung reflexivity. Symmetry is also easy kapag si A ay equivalent kay B. Ibig sabihin merong bijection from A to B. Okay. So para mapakita na si B ay equivalent kay A to satisfy symmetry, pwede nyo sabihin, si F ay bijective. So ibig sabihin si F inverse ay bijective din. Alright? And F inverse is a function from capital B to capital A. So you can say may nag-exist na bijection sa pagitan ni B or mula kay B papunta kay A. And that is the inverse of the bijection we used in order to justify that A is equivalent to B. All right? Tapos sa transitivity, okay? Sa transitivity naman, A related to B. Ibig sabihin may bijection little f between A and B or from A to B. Tapos halimbawa si B ay equivalent din kay C. So that means by definition of equivalence, there exists a bijection G coming from B until C. And then, para mapakita na si A ay equivalent kay C, kailangan lang nating gamitin yung G circle F as the bijection coming from A papunta kay C. So therefore, it is it can be shown that by using this bijection that equivalence is transitive. Dahil na-satisfy niya yung tatlong properties ng isang equivalence relation, then tilde is an equivalence relation, or equivalence is an equivalent. Equivalence is an equivalence relation. All right? Now, some other terminologies used for equivalent sets: equipolant, or equipotent, similar, or equinumerous. Usually I use the term equipolant or equipotent Kasi parang parang matalino silang pakinggan. Pero pag sinabi mo talagang equivalent, magkasing dami lang sila. Actually, the serious reason why I usually use equivalent as my term for equivalence, kasi parang meron tayong laging attached idea about equivalence. Napakaraming, especially if you're talking to a layman or to somebody who didn't take Math 101 in the same class as we are, marami kasing notion ng equivalence ng mga sets. So, kaya to further distinguish, equivalence, meaning the existence of a one-to-one correspondence between the two sets, I am more biased towards using the term equipolant. So si equipolant yung bias ko dun sa slew of synonyms for equivalence. All right? Okay, some quick examples. In example 3, we consider the set G, which is the closed interval 0, 1. So this would be the set of all numbers between 0 and 1, 0 and 1 included. And the set H, which is the closed interval 2 to 5. And then you can show that the function f from G to H defined by the linear function 3x plus 2 is bijective. Therefore, we can say that G is equivalent to H. So, or G is equivalent to H. So, in a nutshell, you can think of, magkasing dami pala yung laman ni closed interval 0, 1 at ni closed interval 2 to 5. Which is a little bit of mind-boggling kasi alam natin pagka dinrawing natin sa real number line, ang haba ni closed interval 0, 1 ay 1. Tama? From 0 to 1, ang length niya ay 1 unit. Ang length ng interval 2 to 5 ay 3. Pero according to this definition, magkasing dami lang pala yung laman ng closed interval 0, 1 at ni closed interval 2 to 5. Why? Because for every element of 0, 1, we can find a unique partner kay 2, 5. And vice versa, for every element of the closed interval 2 to 5, hindi tayo mauubusan ng pwedeng i-partner sa kanya na unique element ng interval 0, 1. And by that definition, G and H, if you will be talking to a layman, pwede nyo sabihin, magkasing dami sila ng laman. At ang basihan natin doon, these two sets are equipolant. Okay? So minsan yun yung mahirap tanggapin na magkasing dami lang sila ng laman pero pag dinrawing ko siya sa real number line, mas mahaba yung set H kaysa kay set G. But again, since merong one-to-one correspondence, may basihan tayo para sabihin na sila ay magkasing dami lamang ng laman. Alright? So siguro yan yung unang mind-boggling fact na makikita natin today. So this is just the beginning. So any questions so far? Okay. Actually, kaya ako tinanong, kailangan ko ng excuse para magsip uli ng kape. Alright. So another mind-boggling example here. So let's consider capital N to be the set N, the set of natural numbers, which we knew from last time sila ay mga ano lang yan, the minimal successor set. Okay? Tapos kunin natin yung set of all positive natural numbers, or actually hindi pala, set of all even natural numbers. So the set of all even numbers actually ay equivalent sa set of natural numbers, which is a little bit of hard to accept siguro for a layman kasi paano magiging magkasing dami yung capital N at saka yung set of all even natural numbers we denote by 2n, where in fact we know that the set 2n is a subset, actually not just a subset, it is a proper subset of the set of natural numbers, and yet 2n is equivalent with the set of natural numbers. Ibig sabihin, magkasing dami lang sila ng laman. So, ang challenge dito ay makapagpakita tayo ng one-to-one correspondence sa pagitan ni n at saka ni 2n. Alright? Siguro pagbaliktarin ko to, hindi, okay lang naman pala na ganyan yung itsura niya. So, what could be a nice one-to-one correspondence that we can attach to it? So, pwede natin gawin ganito yung partnering. Alright? Kailangan ko lang kasi mag-imbento ng one-to-one correspondence, diba? So, 2n, kung isusulat ko siya in roster method, siya si 0, 2, 4, 6, 8, and so on. Tapos si capital N, siya ay si 0, 1, 2, 3, 4, and so on. Okay? Now, I can do the correspondence this way. I will assign 0 to 0, assign 2 to 1, assign 4 to 2, assign 6 to 3, assign 8 to 4, and so on. So essentially, if I have a number 2k over here, I will assign it to the number k. And this mapping every even natural number 2k to the number k is a one-to-one correspondence. And so we can say na equipolant yung set of all positive even integers sa set of natural numbers, even if proper subset ni n si 2n. Siguro sa layman, hindi niya ito matatanggap. Paano naging magkasing dami si n at saka si 2n? Pwede mo sabihin sa kanya, sige, bigyan mo ako ng 2n, bigyan mo ako ng isang positive natural number, ibibigay ko yung kapartner niya ni n. Tapos your baliktaktakan o yung palitan niyo ng mga elements, hindi yan matatapos kasi sa kahit anong ibigay niyang natural even natural number sa'yo, may maibabalikan na unique na natural number. You'll just need to divide whatever the challenge is by 2. You get the corresponding unique partner from the set of natural numbers. Okay? So ito yung parang mind-boggling about the concept of infinity. All right? Now actually, n is also equivalent to kn, where k is any integer. So, multiples of 3, multiples of 4, multiples of 5, they will always be equivalent with the set of natural numbers. Okay? And then sa exercise 5, it says that the open interval, negative pi over 2 to pi over 2 is equivalent to the set R, which is again mind-boggling kasi ito ay isang interval na ang haba lamang ay pi units. Bakit siya magiging equivalent sa set of all real numbers? So kung idodrawing mo yung negative pi over 2 to pi over 2, isa lang siyang maliit na segment ng real number line. And yet exercise 5 is telling us na hindi, magkasing dami lang yung laman ng open interval na yan at saka nung set of real numbers. So can you guys think of a one-to-one correspondence that we can use in able to show this? So pag binigyan ko kayo ng isang element ng open interval negative pi over 2 to pi over 2, kailangan bigyan nyo ako ng real number. And vice versa. Pag binigyan ko kayo ng real number, kailangan hanapin nyo yung pre-image niya dun sa interval. Any idea? Or any hula? Alright. Kung walang hula, pwede nyo itry yung tangent. So define f of x to be tangent of x on the x belonging to negative pi over 2 to pi over 2. Di ba ang graph ng tangent ay asymptotic sa negative pi over 2 to pi over 2? So parang ganito yung graph niya. Ito yung asymptotes niya sa negative pi over 2 to pi over 2. So negative pi over 2 to pi over 2. Alright? Tapos, pag binigyan ko kayo ng isang number, sa pagitan ni negative pi over 2 hanggang pi over 2, lagi kayong may real number na maibabalik sa akin, which is the tangent of that real number. Tapos ang domain ng function na to from negative pi over 2 to pi over 2 is the set of all real numbers. So ibig sabihin, pag binigyan nyo ako ng isang element ni negative pi over 2 to pi over 2, pwede ko kayong bigyan ng isang unique real number, which is the tangent of the challenge that you issued, and that correspondence actually is a one-to-one correspondence. Okay? Kaya equivalent ang negative pi over 2 to pi over 2 papunta kay R. Pero mamaya makikita natin na ang open interval 0, 1 ay hindi equivalent sa set of natural numbers. There could be no one-to-one correspondence between the set of natural numbers and the open interval 0, 1. Ibig sabihin, though alam natin na infinitely many yung laman nila, though hindi ko pa na-define ano yung ibig sabihin ng infinitely many, pero hindi pala magkasing dami yung set n kaysa kay set sa closed interval 0, 1. Alright, which is another mind-boggling fact. So kaya napaka-interesting ng konsepto ng infinity. right? Now, at this point, we will define what a cardinal number is. Okay? Now, we will pick a universal set U. Tapos, ang gusto nating pag-usapan ay yung mga subsets ni capital U. Kasi doon ko i-define yung cardinal number. Okay? Now, we have seen that equivalence is an equivalent relation on the power set of U. All right? So, dahil alam natin na isa siyang equivalence relation, pwede kong i-define yung cardinality ng isang subset ni U as the equivalence class of A. All right? So, kung meron kang isang subset ni U, okay? Tapos yung alam natin na yung equivalence relation, yung equivalence relation ay isang equivalence relation on the power set of U. I-define natin yung cardinal number of A or the cardinality of A to be the equivalence class induced by tilde having A as a member. So remember dun sa problem set 3.1 yun, nakapag-define kayo ng equivalence classes. So yung equivalence classes na yon, with respect to the equivalence relation equivalence, sila yung tinatawag nating cardinal number o yung cardinality ng isang set. Siguro sa elementary algebra, ang definition nyo sa cardinality ng isang set ay kung ilan yung laman niya. Formally, in formal mathematics or in the axiomatic development of things, ang cardinality ng isang set ay isa ring set. Siya yung equivalence class containing A induced by tilde. So, ibig sabihin, ito yung set ng lahat ng mga sets na kasing dami ni A yung laman. Tapos, para lang mas mapadali ito, ang hirap niyang ipaintindi siguro sa high school or sa beginning math student. So, kaya binigyan na lang natin ng symbol yung cardinality. Yung cardinality, ni-represent natin by a number. Kung ilan yung laman ni capital A. But where in fact, the very definition of the cardinality of A, it is a set. Just as like how we define natural numbers. Di ba? Yung natural numbers, alam natin ang laman niya ay sets. Siya yung minimal successor set. So ang laman niya siya si omega. Nirelabel lang natin si omega to be 0, 1, 2, 3, 4, 5. Pero ang laman niya talaga ay empty set. The set containing empty set. The set containing the empty set. And the set containing the empty set. And so on. Ganon din yung cardinality. Isa rin siyang set, pero for brevity and convenience, imbes na tingnan natin siya sa equivalence classes, denote natin yung cardinality ng isang set as kung ilan yung laman ng sets na yon, ng mga sets dun sa equivalence class na yon. Okay? The cardinality of a set or the cardinal number of a set is denoted by this, like the absolute value of A or the size of the set A, or card of A or cardinality of A. Right? So maraming definitions ng cardinal number, pero among all those definitions of the cardinal numbers, laging eto yung basehan. The cardinal number of A is equal to the cardinal number of B if and only if A is equivalent with B. Ibig sabihin, kung magkasing dami sila ng laman. Okay? Now, meron tayong equivalence relation. Now, pwede tayo mag-define ng isang partial order sa set of all subsets of the universal set U. Yun yung nasa definition 8. Now, dito, dinidefine lang natin yung relation domination. Okay? So we say that a set A is dominated by a set B, or B dominates A if A precedes B. Okay, ito yung notation lang naman natin sa partial order, so general partial order. So we will define this such that this will happen if and only if the cardinal number of A is less than the cardinal number of B. So ibig sabihin, i-dominate ni B si A kung mas marami yung laman ni B kaysa kay A. Alright? And I just need this to state this famous result, the Schroeder-Bernstein theorem, which says na anti-symmetric yung actually hindi pala anti-symmetric to eh. Medyo mas generalized version ng anti-symmetry. If B dominates A and A dominates B, then A is equivalent to B. All right. Though I don't want to focus with these technical results right now kasi ayoko masyadong mabigat yung last session natin for the semester. But I would be remiss if I will not mention at least the Schroeder-Bernstein theorem, because this is one of the fundamental theorems in in the context of cardinal numbers. So if you want to really appreciate Schroeder-Bernstein, pwede nyo sundan yung discussion dito sa work text. All right. Pero yun, I wanna skip this one. Tapos ito yung gusto kong puntahan. Transfinite cardinals and countable sets. Pero are you guys still there? Because Teams is notifying me that I have bad connection, unstable connection. Napuputol-putol ba ako?
Hindi naman, sir.
Hindi
Okay
naman
lang.
po, sir.
Okay, thank you. So may mga tanong ba so far? Or masyado na bang mabigat yung discussion? The thing is, kailangan ko siyang i-lay down yung theoretical background. Though, again, do not worry about it. So siguro sa essay type ko ilalagay yung questions coming from this section. All right? Okay, dito sa transfinite cardinals and countable sets, dito natin i-discuss yung konsepto ng infinity. Okay? Now, what is an infinite set? Ginagamit na natin yung term, I guess, early on in the course, but we haven't defined formally what an infinite set is, right? And that comes in definition 1. It says here that a set is infinite if it is equivalent to a proper subset of itself. So, ang isang set ay nagiging infinite kapag makakahanap ka ng isa niyang proper subset na equivalent sa kanya. For instance, we have seen that the set of natural numbers is equivalent to one of its proper subsets, namely the set of all even natural numbers. All right. So we can say that the set N is infinite kasi equivalent siya sa isa niyang proper subset. Also, we have seen that the open interval, negative pi over 2 to pi over 2, even though it is finite, is equivalent or equivalent to the set of all real numbers. So we can say that the set of real numbers is another infinite set. Okay, how about the integers? How can you prove that the set of integers is an infinite set? Actually, we can show that the set Z is equivalent with the set N. Magkasing dami, sort of, yung laman ni N at saka ni even integers. And saka ni integers. So, ibig sabihin, si set of all integers ay infinite set din. How can we do the pairing? Well, pwede nyo siyang gawin ganito. We just need to be clever in pairing up these elements. So, si Z, okay. Kailangan ko ng magandang paraan ng pagsusulat kay set of integers, right? If I will write it as dot, 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 negative 2, negative 1, 0, 1, 2, dot, dot, dot. Tapos gusto kong maka-create ng one-to-one correspondence with 0, 1, 2, 3, 4, and so on. Mahihirapan ako kung ganito ko siya titingnan. Kasi sino yung ipe-pair ko kay 0? Pag pinair ko si 0 kay 0, si 1 pinair ko kay 1, si 2 pinair ko kay 2, si 3 pinair ko kay 3, mauubos yung set of natural numbers natin, pero hindi natin mamamap o hindi natin mabibigyan ng kapartner yung mga negative integers. So that might lead you to believe na baka naman pala hindi sila magkasing dami ng laman. But again, the only requirement is the existence of one-to-one correspondence. Makakita ka lang ng isang bijective function from Z to capital N. The pairing that I just tried to do is not bijective, but it is just one of the candidates para maging isang bijection. Isa lang siyang function. Well, I can do the pairing this way, or the listing of Z this way. Isulat ko si Z in a nice way. Sulat ko siya na 0, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, and so on. Okay? So, ibig sabihin, shortcut lang yung plus or minus sa pagsusulat ko ng negative 1, 1, tapos ito ay negative 2, 2, and so on. Alright? And then, I'll do the pairing this way. Si 0, si 0, imamap ko siya kay 0. Si 1, imamap ko siya kay negative 1. Si 2, imamap ko siya kay positive 1. Si 3, imamap ko siya kay negative 2. Si 4, imamap ko siya kay positive 2. Si 5, imamap ko kay negative 3. Si 6, imamap ko kay positive 3, and so on. With this mapping, I am sure that I can exhaust the set of all natural numbers as well as the set of integers, meaning every integer will be given a unique partner sa set of natural numbers and vice versa. Therefore, that assignment will be a one-to-one correspondence. So we can say that n and z are equipolant with each other, and since n is a proper subset of z, ibig sabihin si z ay infinite set din. All right? Now, if a set is not infinite, then it is said to be finite. Napakasimple ng definition ng pagiging finite, no? Kung hindi siya infinite, syempre siya ay finite. Okay? Now, we will now define, kasi magkakaroon tayo ng iba't ibang konsepto ng infinity. Alright? So, tawagin natin yung, ang cardinality ng isang infinite set ay tinatawag nating isang infinite cardinal number. Okay? Kaya lang, tingnan nyo yung term, yung article, and yung ginamit. Ibig sabihin, posible magkaroon ng iba't ibang infinite cardinals. Though, kasi mapapakita natin na yung set n ay hindi equivalent kay R. So, ibig sabihin, hindi equivalent si n at saka si R. So, yung cardinal number o yung infinite cardinal number para kay n ay hindi equal sa cardinal number or cardinal infinite number para kay R. So, pare silang infinite yung laman, pero magkaiba silang level ng infinity. So, you can say na mas maliit yung level ng infinity o ng infinitude ni n kaysa sa pagiging infinite ni R. So, yung infinity pala, meron pa rin silang mga levels. Alright? Now, to distinguish this, we adopt several symbols. So, the cardinal number for the set of natural numbers, which is the smallest level of infinity, is called Aleph null or Aleph naught. Okay? So, denoted by this letter here. This is the Hebrew letter, Aleph. Parang ito yung first letter ng Hebrew alphabet. Tingnan nyo sa math, no? Nauubusan na tayo ng letters. Nauubusan natin yung Latin letters o yung English letters. Ginagamit na rin natin yung mga Greek letters. Tas ngayon, nasa Hebrew letters na tayo. Alright? So, Aleph null, yung cardinality ng set of natural numbers. So, that means, since the set of integers is equivalent with n, ibig sabihin ang cardinality o ang cardinal number ng z ay Aleph null din or Aleph 0. Okay? Tapos, pero yung R, dapat iba yung level ng infinity ni R. Actually, ang cardinal number ni R is Aleph. Ang hirap isulat ng Aleph. Hindi ako sanay magsulat niya. So, ang pangit. So, yeah, Aleph 1. So, Aleph 1 yung cardinality ni R. All right? Now, if n is a finite cardinal, so yung cardinality ng isang finite set ay mas maliit kaysa kay Aleph null. All right? So, Aleph null is also a number. It's an infinite cardinal, so it is greater than any finite number. Okay? And then some more definitions that I will throw in the air just for your appreciation of the terms. Pag meron kang set D na equivalent sa N, ang tawag natin dun sa cardinal number ni D or ang tawag natin kay D ay isang denumerable set. So any set that is equivalent to N is said to be denumerable. So ibig sabihin, the set of integers, the set of even natural numbers, the set of multiples of 5, they're all denumerable sets. And kapag ka siya ay denumerable set, ang cardinality niya ay Aleph null. Alright? Kapag kasi ang isang set ay non-denumerable, kapag ka siya ay infinite, pero hindi siya equivalent kay n. Example ng non-denumerable set ay set of real numbers. Tapos another example is the set of irrational numbers, which we will show later. Kasi hindi equivalent ang set of all irrational numbers kay capital N. So non-denumerable ang set of irrationals. Now, ito pa yung mga terms. Medyo marami nga yung terms dito, no? A set is called countable if it is finite or denumerable. Tinawag siyang countable kasi kaya mo siyang bilangin. Wala nga lang assurance na matatapos kapag bibilang. Of course, if your set is finite, okay? Kung finite yung set, definitely countable yon. Kasi kaya nating bilangin yung mga elements niya. Say, the set of all letters in the English alphabet. So you can count the numbers, you can count the members of that set, 1, 2, 3, 4, 5, hanggang 26. So that's countable. Tapos ang set of all natural numbers then ay countable. Kasi pwede mo silang bilangin. So si 0, siya yung first element. So siya yung 1, 2, 3, 4, 5. Sunod-sunod yung pagbibilang. Hindi nga lang tayo matatapos sa pagbibilang. Pero that doesn't tell us that hindi siya countable. Countable siya, hindi nga lang tayo matatapos. So kapag siya ay finite o kaya siya ay denumerable, ibig sabihin siya ay countable. Ang isang set ay hindi countable kapag hindi siya denumerable. Alright? Pagka, halimbawa, ang set of all irrational numbers, hindi natin kayang bilangin yan. Ang set of real numbers, hindi natin kayang bilangin yan. Bakit? Kasi halimbawa, mag-start ka kay 0. Si 0 yung unang real number na bibilangin mo. Sino yung isusunod mo sa kanya? Si 1/2 ba? Isusunod mo ba si 1/3? Isusunod mo ba si 1 over 100? Si 1 over 1,000? We cannot definitely create a scheme in order to count all the real numbers. Kasi from 0, we don't know where to go next. At walang ibang paraan para mabilang yung mga yung mga real numbers. Kaya the set of all real numbers is uncountable in layman's term. Pero klaro, sa definition 5, technically, kailan siya nagiging uncountable pag hindi siya denumerable. Alright? So, yes, these are some examples of denumerable sets. Okay, it's easy to see that they are. But the nice examples ay nabanggit ko na rin verbally. Sa illustration 27, nandito yung pagpo-prove na si Z ay denumerable. Finormalize niya yung argument natin kanina kung paano i-construct yung one-to-one correspondence between the set of integers and the set of natural numbers. So you can try this out. Pero yung essence ng proof na to, napakita ko na kanina with yung drawing natin ng kung paano natin sinulat si Z at paano natin siya pinartner sa mga natural numbers. Now, the set of rational numbers is also denumerable. And this is quite interesting. Paano naging denumerable yung set of all rational numbers? So, yung mga fractions. Paano natin kayang bilangin yung mga fractions? Ibig sabihin, equivalent siya kay capital N. Now, how can this be done? There was a very ingenious way that is attributed to, I think this was Cantor. Ito yung ginawa ni Cantor para mapakita na kaya mong bilangin yung mga fractions. Ang ginawa niya, gumawa siya ng infinite spreadsheet. Okay? So, yung mga column headers, sila yung 1, 2, 3, 4, 5, and so on. Yung row headers, sila yung 1, 2, 3, 4, 5, and so on. So, ito ay mga natural numbers, ito ay mga natural numbers, then except 0. Si 0, pwede mo nang ilagay dito. Okay? Tapos, yung mga entries sa column, sila yung row number divided by the column number. So, itong nandito, siya yung 1 over 1. Tapos, yung nandito, siya yung 1 over 2. Tapos, ito ay 1 over 3 kasi nasa first row, third column siya, and so on. Okay. Tapos, lagay ko na dito si 0 para masabi natin na equivalent talaga siya sa set of all natural numbers. Tapos, di ba, kailangan mapakita natin siya na equivalent sa n. So, dapat sa bawat natural number, meron tayong maibigay na kapartner. But would you agree that dito ay nakasulat na lahat ng posibleng fractions? Alright? Kasi para maging rational number, dapat kaya natin siyang isulat as a natural number over a natural number. Okay? Actually, kulang pala to. Wala yung mga plus or minuses, no? So, lagay ko dito plus or minus, plus or minus, plus or minus, plus or minus. So imagine lahat dito magkakaroon ng plus or minus. Okay? And so on. So, would you agree? Or I think by now you should agree or you can agree na dito na-exhaust ko na lahat ng mga rational numbers. Kasi lahat ng rational numbers ay integer over integer. And by this scheme, I have a nice way of writing everything. Okay? Now, nasan yung one-to-one correspondence with the set of natural numbers? Well, kung ganito mo siya i-assign, ito yung i-assign ko kay, ito yung i-assign ko kay 0, ito yung i-assign ko kay 1, kay 2, kay 3, kay 4, kay 5, kay 6, kay 7, kay 8. Kung by row kayo nag-assign, hindi kayo matatapos kasi hindi pa kayo tapos sa first row, na-exhaust nyo na lahat ng natural numbers. Paano ka pa pupunta sa second row? So medyo mahirap i-imagine na gano'n yung mangyayari. Okay? Kasi parang hindi tayo makakaalis sa first row. Hindi magiging surjective yung correspondence seemingly hindi magiging surjective yung one-to-one correspondence na i-define natin. Okay. Pero sabi ni Cantor, bakit ganun ka magbibilang? Pwede mo siyang bilangin ng ganito. Okay, 0 is assigned to 0. I assign 1 over 1 kay 1. Tapos si 1 half, i-assign ko kay 2. Si negative 1 half, i-assign ko kay 3. Tapos si 2, i-assign ko kay 4. Tapos si 5, i-assign ko kay negative 2. And then I'll go here. I'll assign this. I'll assign this. Then diagonal yung process. Ganito mo siya bibilangin. Okay? And in this way, madadaanan natin lahat ng element, lahat ng rational numbers. May mga sobra pa nga eh. Kasi yung iba, halimbawa yung 2 over 1, kaparehas lang siya ng 4 over 2. So kung nabilang mo na siya before, pwede mo siyang burahin dun sa table or ligtangan siya dun sa pairing. Pero with the diagonal, the ingenious diagonal pairing, madadaan natin without any sweat lahat ng natural numbers, lahat ng rational numbers. That's why we can say that the set of all rational numbers is denumerable kasi equivalent siya kay capital N. However, the set of irrationals ay hindi denumerable. So yun yung siguro via video ko na lang ipapakita. Okay. Now, I will probably end the discussion here with the uncountable sets, but mag-overtime na naman ako. So if you guys have a class at 10 a.m., then you can leave the meeting and just watch the last portion of the recording. I'll play 2 videos, nice videos illustrating the concept of infinity. So pwede nyo na siyang balikan later or panoorin nyo na lang siya sa YouTube. So pero maganda kasi yung animation niya about the levels of infinity. But before going there, gusto kong sabihin itong, I want to talk about the continuum hypothesis a little bit. Okay. Now, Theorem 6.3.1 tells us na yung cardinal number ng isang set ay laging mas maliit sa cardinal number ng kanyang power set. Okay. This is obvious. We have proven this inequality for the case of finite sets. Halimbawa, ang cardinality ni A ay n. Ibig sabihin, si set A ay may n na laman. We have proven via mathematical induction, or kayo pala dun sa isang problem set natin, na ang cardinality ng power set ni A ay 2 to the power n. Okay? So definitely, n is less than 2 to the power n for any value of n. So laging mas marami, at least on a finite case, yung laman ng power set ni A kesa sa laman ni A. So a set A is not equivalent to its power set. Okay? And this is also true for infinite sets. Yun yung sinasabi ng Theorem 6.3.1. And the proof used the domination relation based on equivalence na ini-skip ko kanina. So I'll skip the proof, pero yun yung essence ng theorem 1 dito. Ang cardinality ng isang set ay mas maliit, strictly mas maliit kesa sa cardinality ng kanyang power set. Okay? And then okay. So, the set of irrationals, yun yung papakita sa atin ng video mamaya. And then, yeah. Ibig sabihin pala, okay. So, in that sense, actually, hindi natin ipapakita, pero ang set of all real numbers ay hindi equivalent kay n. Alam na natin yan kasi hindi denumerable si r, pero siya ay equivalent sa power set ni n. So, ibig sabihin ng cardinality ni r ay dapat mas malaki sa cardinality ni n. Right? So, ang cardinality ni n, siya yung aleph null. Cardinality ni r ay si aleph 1. So, we can say that aleph, ang pangit ng aleph ko, itong x ay aleph yan. Ang aleph 1 ay 2 to the power aleph null. So, yan yung parang inequality. Yan yung parang equation natin. Yung para sa cardinal number aleph 0 at aleph 1. Right? Kasi nga, parang sinunod ko yung cardinality ng power set, 2 to the power n. Si n ay may aleph 0 na laman. So yung power set niya, which is r, ay may laman na 2 to the power aleph null. Pero yung 2 to the power aleph null, tawagin nating aleph 1. Okay, what is the continuum hypothesis? The continuum hypothesis is saying there is no cardinal number beta such that beta is strictly between aleph 0 and aleph 1. So ano yung implication ng continuum hypothesis? Sinasabi ng continuum hypothesis na walang set na mas maraming laman kesa kay n, pero mas kokonte yung laman kay capital N. So parang walang makakasingit sa pagitan ni aleph 0 at ni aleph null. We cannot find a proper subset of R and a proper superset of N which is not equivalent to either N or R. Okay? So, sabihin, wala kang pagka meron kang isang infinite set na hindi mas paano ba natin i-laymanize to? Halimbawa, meron kang isang set na mas maraming laman kaysa kay set n. Ibig sabihin at least ang value niya na o ang cardinality niya ay aleph 1. At least kasing dami yon ng set of real numbers o ng laman ng set of real numbers kasi nga ang sinasabi ng continuum hypothesis, wala nang dapat cardinal number sa pagitan ni aleph 0 at ni aleph 1. However, mapapansin nyo, ang title sa kanya ay hypothesis. Hindi siya continuum theorem kasi hindi siya proven. Alright? And actually, it was shown by, I think it was shown by Cantor. Double check ko nga yung Wikipedia page. Binabasa ko siya kanina. Ayan, there you go. Wala siya dito. Na-close ko yung Wikipedia page. Pero si Cantor yata yung nagpakita, check me on this, si Cantor yung nagpakita na hindi contradictory yung continuum hypothesis sa ZF set theory or sa Zermelo-Fraenkel set theory. He did that by showing that yung negation ng continuum hypothesis ay hindi theorem sa Zermelo-Fraenkel set theory. So hindi ma-prove sa Zermelo-Fraenkel set theory yung existence ng beta. So ibig sabihin yung continuum hypothesis ay hindi niya kino-contradict yung Zermelo-Fraenkel axioms kasi hindi natin kayang i-prove na may nag-exist na beta. Hindi natin kayang i-disprove yung continuum hypothesis using the Zermelo-Fraenkel axioms. And that happened, I think, in the 1940s lang. Also, check me on that. Nakalimutan ko yung Wikipedia page na i-open. Tapos, in 1963, pinrove naman ni... sorry. I forgot the name of the mathematician. Somebody proved, sorry, nakalimutan ko siya. Somebody proved that yung continuum hypothesis ay hindi ang continuum hypothesis ay independent mula sa Zermelo-Fraenkel axioms o sa ZF axioms, meaning hindi kayang i-prove ng Zermelo-Fraenkel set theory ang continuum hypothesis. So on the one hand, Cantor showed na the continuum hypothesis is not contradictory, or the continuum hypothesis is in fact consistent with the Zermelo-Frankel axioms, but this other guy proved that the continuum hypothesis is independent, meaning it cannot be proved using the Zermelo-Frankel set theory. Ayan, nalito tuloy ako. Si Gödel ba yun o si Cantor? Si Gödel yata yung nagpakita. Yeah, I think it's Gödel na nagpakita na yung continuum hypothesis ay consistent sa Zermelo-Frankel set theory. Tapos yung isang guy siya yung nagpakita na independent, yung continuum hypothesis. So in the current set theory that we have, we cannot prove whether or not the continuum hypothesis is true. Kaya siya hypothesis lamang. Nobody can tell if this is true or not. And that's one limitation of the Zermelo-Frankel set theory, which is to be expected because Zermelo-Frankel set theory is desired to be a consistent system. Tapos sabi ng incompleteness theorem ni Gödel, walang axiomatic system ang pwedeng maging consistent and complete at the same time. So definitely there are statements that cannot be proved in that axiomatic system. And an example of which for the Zermelo-Frankel system is the continuum hypothesis. All right? So I think that's the end of this discussion. Any questions? Medyo mabigat ba yung discussion today? Maraming terms, but I hope you get an appreciation about it. And again, don't worry, don't anticipate a proving question coming from this session. Okay? Now, kung walang questions, so you can guys stay and then I'll play this video. Siguro pwede natin pag-usapan after. Let me just play this one. This is a nice video. Oops. Ulitin ko pala. Hindi ko na-click yung share with audio. Okay, hopefully may audio to pag pinlay ko. Kindly call my attention kung walang audio. Okay, let me play this now.
In the 1920s, the German mathematician David Hilbert devised a famous thought experiment to show us just how hard it is to wrap our minds around the concept of infinity. Imagine a hotel with an infinite number of rooms and a very hard-working night manager. One night, the infinite hotel is completely full, totally booked up with an infinite number of guests. A man walks into the hotel and asks for a room. Rather than turn him down, the night manager decides to make room for him. How? Easy. He asks the guest in room number 1 to move to room 2, the guest in room 2 to move to room 3, and so on. Every guest moves from room number n to room number n plus 1. Since there are an infinite number of rooms, there is a new room for each existing guest. This leaves room 1 open for the new customer. The process can be repeated for any finite number of new guests. If, say, a tour bus unloads 40 new people looking for rooms, then every existing guest just moves from room number n to room number n plus 40, thus opening up the first 40 rooms. But now, an infinitely large bus with a countably infinite number of passengers pulls up to rent rooms. Countably infinite is the key. Now, the infinite bus of infinite passengers perplexes the night manager at first, but he realizes there's a way to place each new person. He asks the guest in room 1 to move to room 2. He then asks the guest in room 2 to move to room 4, the guest in room 3 to move to room 6, and so on. Each current guest moves from room number n to room number 2n, filling up only the infinite even-numbered rooms. By doing this, he has now emptied all of the infinitely many odd-numbered rooms, which are then taken by the people filing off the infinite bus. Everyone's happy, and the hotel's business is booming more than ever. Well, actually, it is booming exactly the same amount as ever, banking an infinite number of dollars a night. Word spreads about this incredible hotel. People pour in from far and wide. One night, the unthinkable happens. The night manager looks outside and sees an infinite line of infinitely large buses, each with a countably infinite number of passengers. What can he do? If he cannot find rooms for them, the hotel will lose out on an infinite amount of money, and he will surely lose his job. Luckily, he remembers that around the year 300 BCE, Euclid proved that there is an infinite quantity of prime numbers. So to accomplish this seemingly impossible task of finding infinite beds for infinite buses of infinite weary travelers, the night manager assigns every current guest to the first prime number, 2, raised to the power of their current room number. So the current occupant of room number 7 goes to room number 2 to the 7th power, which is room 128. The night manager then takes the people on the first of the infinite buses and assigns them to the room number of the next prime, 3, raised to the power of their seat number on the bus. So the person in seat number 7 on the first bus goes to room number 3 to the 7th power, or room number 2187. This continues for all of the first bus. The passengers on the second bus are assigned powers of the next prime, 5. The following bus, powers of 7. Each bus follows powers of 11, powers of 13, powers of 17, etc. Since each of these numbers only has 1 and the natural number powers of their prime number base as factors, there are no overlapping room numbers. All the bus's passengers fan out into rooms using unique room assignment schemes based on unique prime numbers. In this way, the night manager can accommodate every passenger on every bus, although there will be many rooms that go unfilled, like room 6, since 6 is not a power of any prime number. Luckily, his bosses weren't very good in math, so his job is safe. The night manager's strategies are only possible because while the infinite hotel is certainly a logistical nightmare, it only deals with the lowest level of infinity, namely the countable infinity of the natural numbers, 1, 2, 3, 4, and so on. Georg Cantor called this level of infinity Aleph 0. We use natural numbers for the room numbers as well as the seat numbers on the buses. If we were dealing with higher orders of infinity, such as that of the real numbers, these structured strategies would no longer be possible, as we have no way to systematically include every number. The real number infinite hotel has negative number rooms in the basement, fractional rooms, so the guy in room 1/2 always suspects he has less room than the guy in room 1, square root rooms like room radical 2, and room pi, where the guests expect free dessert. What self-respecting night manager would ever want to work there, even for an infinite salary? But over at Hilbert's Infinite Hotel, where there's never any vacancy and always room for more, the scenarios faced by the ever-diligent and maybe too hospitable night manager serve to remind us of just how hard it is for our relatively finite minds to grasp a concept as large as infinity. Maybe you can help tackle these problems after a good night's sleep, but honestly, we might need you to change rooms at 2 a.m.
Okay, so I think that's a nice illustration of yung mga equivalents or yung one-to-one correspondences na tinatry ko kaninang i-illustrate. So I hope you guys enjoyed that video. But before we play the other video, ayan, na-search ko na ulit. Si Kurt Gödel, yung nagpakita noong 1940 na yung continuum hypothesis ay consistent with CF set theory, na hindi natin kayang i-prove na mali yung continuum hypothesis sa Zermelo-Fraenkel set theory. Tapos si Paul Cohen, yung nagpakita noong 1963. And imagine, these are just recent, within the last 100 years, right? In 1963, Paul Cohen proved na hindi natin kayang i-prove yung continuum hypothesis using the Zermelo-Fraenkel axioms. So, yeah. So ibig sabihin, si continuum hypothesis cannot be proved or disproved using Zermelo-Fraenkel set theory. So kailangan nyo mag-imbento ng panibagong mathematics o panibagong set theory kung gusto nyong i-prove o i-disprove yung continuum hypothesis. Right? So just to end, parang isang additional level dun sa Hilbert's Infinite Hotel. So tingnan natin tong isa pang video. This is from Veritasium. So hindi ko siya i-play from the beginning kasi yung first portion ng video na to ay katulad nung TED video na napanood natin. So, simulan ko lang siya dun sa part na hindi na cover nung unang video. Alright? So, again, let me share that. Okay. Okay, again, call my attention kung walang audio, pero I hope this is good.
Everybody. And that's the beauty of infinity. It goes on forever. And then all of a sudden, more infinite buses show up. Not just one or two, but an infinite number of infinite buses. So what can you do? Well, you pull out an infinite spreadsheet, of course. You make a row for each bus, bus 1, bus 2, bus 3, and so on, and a row at the top for all the people who are already in the hotel. The columns are for the position each person occupies. So you've got hotel room 1, hotel room 2, hotel room 3, etc. And then bus 1, seat 1, bus 1, seat 2, bus 1, seat 3, and so on. So each person gets a unique identifier, which is a combination of their vehicle and their position in it. So how do you assign the rooms? We'll start in the top left corner and draw a line that zigzags back and forth across the spreadsheet, going over each unique ID exactly once. Then imagine you pull on the opposite ends of this line, straightening it out. So we've gone from an infinite by infinite grid to a single infinite line. It's then pretty simple just to line up each person on that line with a unique room in the hotel. So everyone fits, no problem. But now a big bus pulls up, an infinite party bus with no seats. Instead, everyone on board is identified by their unique name, which is kind of strange. So their names all consist of only 2 letters, A and B, but each name is infinitely long. So someone is named A, B, B, A, 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 and so on forever. Someone else is named A, B, A, B, A, B, A, B, A, B, etc. On this bus, there's a person with every possible infinite sequence of these 2 letters. Now, A, B, B, A, 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 A.
Okay, hold on. Excuse me muna. So, ito yung parang example kung paano natin mapuprove na yung set of irrational numbers ay hindi equivalent sa n. So, bawat isang passenger nitong bus na to, yung mga pangalan niya A, B, 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 A, pwede siyang isipin as the elements of the irrational numbers. They are non-repeating, non-terminating decimals. So, titingnan natin kung bakit hindi sila ma-accommodate nung Hilbert Hotel, which only has a countable number of rooms. All right? So, let me play the video now.
I'll call him Abba for short. He comes into the hotel to arrange the rooms. But you tell him, sorry, there's no way we can fit all of you in the hotel. And he's like, what do you mean? There's an infinite number of us, and you have an infinite number of rooms. Why won't this work? So you show him. You pull out your infinite spreadsheet again and start assigning rooms to people on the bus. So you have room 1, assign it to ABBA, and then room 2 to AB, 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 AB repeating, and you keep going, putting a different string of A's and B's beside each room number. Now here's the problem, you tell ABBA. Let's say we have a complete infinite list. I can still write down the name of a person who doesn't yet have a room. The way you do it is you take the first letter of the first name and flip it from an A to a B. Then take the second letter of the second name and flip it from a B to an A. And you keep doing this all the way down the list, and the name you write down is guaranteed to appear nowhere on that list because it won't match the first letter of the first name or the second letter of the second name or the third letter of the third name. It will be different from every name on the list by at least 1 character, the letter on the diagonal. The number of rooms in the Hilbert Hotel is infinite, sure, but it is countably infinite, meaning there are as many rooms as there are positive integers 1 to infinity. By contrast, the number of people on the bus is uncountably infinite. If you try to match up each one with an integer, you will still have people left over. Some infinities are bigger than others. So there's a limit to the people that you can fit in the Hilbert Hotel. This is mind-blowing enough, but what's even crazier is that the discovery of different sized infinities sparked a line of inquiry that led directly to the invention of the device you're watching this on right now. But that's a story for another time.
All right, so yeah, I think that's a nice illustration na meron talagang iba't ibang levels of infinity. Some infinities are greater than the other. All right, so and then in the work text, there is some more formal proof na ang set of all irrationals ay hindi equivalent sa set of natural numbers. Tapos dahil yung set of real numbers is the union of the set of rationals and the set of irrationals, that means the set of real numbers is really not equivalent with the set of natural numbers. All right? So yun yung Aleph zero and Aleph null. And if the continuum hypothesis is true, we cannot construct a set whose cardinality is strictly between Aleph 0 and Aleph 1. All right? And I think that's the end of the course. So thank you guys for not only for today, but also for joining in and day out. Actually, I really enjoyed Math 101 this semester, kahit online yung offering. I love the interaction that we had, especially during the first few, actually the good portion of the semester. Sorry, hindi ko nga lang siya na-sustain towards the end because I'm really trying to compress all the remaining materials. Maybe we can suggest to have Math 101 lectures longer. Kunin natin yung isang oras mula sa um, mula sa labs. Baka pwedeng 3 hours yung lecture, 2 hours yung lab, to make it more to make the discussion more longer and more in-depth, all right? Pero, yeah, sabi nga, sino ba tayo nagsabi? Sa chat, sabi ni Mitzi, meron pang ibang courses. Yeah, I hope to see you around the math division. Hopefully you stay in the math, applied math, or MSc program. And definitely there's a big chance that we will be seeing each other again in the long run. So I usually teach advanced calculus classes. I'm teaching, ano pa ba? Yeah, Math 174, numerical analysis. So yeah, I think we will still meet again. But for now, I think this is goodbye. All right, but temporary. So we'll see each other again around. And may utang pa kayong dalawang submissions sa akin. So we have problem set 1 and problem set 4 and the final project. And I hope to get them as soon as you can, so I can give you your final grade. Makikita nyo rin siya via kay Canvas. Okay. So it was nice having you as my students. I hope you enjoyed the course. You got something from it. And yeah, see you around. Bye, everyone.
Thank you po,
Sir, thank you.
All right.
Thank you,
Thank you,
sir. Stay
sir.
Thank you
safe
po,
po.
sir.
Andaya
Thank
pala,
you.
never kayo nagkita sa akin, no?